Hello everyone and welcome to another Würth Elektronik eiSos webinar. My name is Thomas Robock and I will moderate this webinar today. We are very pleased that you took the time to participate in our webinar. The topic of today's webinar is AskPM, the Q&A session with product management about REDCUBE high current contacts on the printed circuit board. Our speaker today is Wladimir Werz, who is working as product manager in the field of REDCUBE at Würth Elektronik eiSos. He will hold today's webinar and answer your questions. Before we start the webinar, I would like to point out one thing. You will be muted during the webinar today. This means that you cannot ask us questions via microphone during the webinar. Nevertheless, you have the opportunity to ask us questions during the webinar at any time via the chat function. You'll find the chat function in the webinar control panel. Today's webinar will be about 45 minutes long overall. The chat questions will be answered directly during the webinar, so you have the chance to directly ask the PM at the momentary point of time. If we are unable to answer all your questions within this time, we will answer them via email after the webinar. If you still have any other questions left after the webinar, just email us at eisos-webinar@we-online.com. We will try to answer all questions promptly. You will receive the link to the presentation as well as to the recording of the webinar only in the next few days. Now I will hand over to our speaker Wladimir, and I wish you an exciting webinar.
Hello and welcome from my side. My name is Wladimir Werz. I am the responsible product manager for the product group REDCUBE, and welcome to the webinar. Let's start together. So we get a lot of different questions from customers regarding the press fit technology, and we have some of these questions in the presentation, but please also ask the questions during the presentation that we can clarify all your question and give you the best solution for your questions. So the main question we get very often from the customers: what is press fit technology in general, and how does this technology work? So what happens when we press the pins into the PCB? So the technology is quite easy. It's a solder-free technology, so we don't have any solder process, and we also don't have any thermal processes. So what we do, we press a massive pin into a via of the PCB, and we have quite high press fit forces. So we have about 100 Newton of press fit force for a PCB thickness of 1.6 millimeter. And because of this force, we generate high friction in the via and generate a cold welding. And this cold welding is the main point of the press fit technology. With this cold welding, we get a really powerful electrical connection, and we create also a gas-tight connection. How the press fit curve is looking like. So we see that when we press the parts into the PCB, we have our way of pressing. So we can see here the peak, and this peak shows us where the pins are coming out of the PCB here at this step. So when the pins are coming out of the PCB, the force is getting down. This means that the press fit, that the cold weld connection is already generated, and at this point we can stop the press fit process because we got already a proper connection in the PCB. We can also see here the force itself. We have a part with 16 pins, and the force is about 1,600 Newton for the whole part. So we are close to this 100 Newton per piece, per pin. And we can also see the range of different parts, and this range is due to different tolerances we have on the part side and also on the PCB side. We get very often the question that we contact only on 4 points, and is this contact area enough to transfer all the currents? So we have different products where we specify some of the products up to 500 amps with only one component, and this question is getting quite often: is it enough or not enough? But we can answer it easily. We can measure the connecting angle of every corner on the pins, and then we can calculate with this angle the total contact area in the PCB. Here is a quite simple formula that we can use for the calculation, and we have the angle. We already measured the angle. We have the P, we know the P. We have the diameter. We know the diameter because we specify the diameter of the via. We have L, it's the thickness of the PCB. And we have 4 because we have 4 corners. So in the brackets, the formula is for this yellow area, but we have 4 corners, so we have to multiply by 4. So if we put the number into the formula, 2 millimeter PCB thickness, for example, 1.475 millimeter diameter of the via, P, and the angle of the connecting area. So finally we get a result of 0.34 square millimeter for this yellow area. And if you multiply it by 4 corners, we get a total area of connection that is bigger as the cross section of the pin itself. So finally we can see on this point that the connecting area itself is not a bottleneck because it's even larger as the cross section of the pin. Thomas, did we get any questions in the time?
Yeah, Vladimir, I have one question here regarding PCB thickness and current. So it states if you have a smaller PCB thickness, then of course the relation between cross-section of the pin and contact area on the PCB is getting worse, I would say. So how to deal with that, and where is the limits?
Yes, what we firstly have to say that if the PCB thickness is a little bit lower, then the result will also be a bit lower. But we compare this connecting area. If I go one step back to the cross section, this connecting area is to the copper, and this connecting area to the copper means that we compare this area of the pin itself, the pins are made of brass, to the connecting area of copper. And copper has 4 times better current carrying capacity. So in general, this area can be 4 times smaller to have the same resistance as in the pin itself. So it doesn't really matter if we use a PCB with less thickness, because the this area is connected to copper. All right.
Thank you, Vladimir. That's all for the moment.
All right. Then I will go on with the other questions we prepared. So another question we get from the customer is about long-term reliability, especially the long-term reliability compared to the solder joints. And we say that the long-term reliability of press fit technology is much better compared to the solder joints. Why? First of all, we see here we contact the copper alloy, the pin made of copper alloy directly to the copper, and we don't have any solder in between. For a solder joint, we have again a copper or copper alloy, but additionally we have solder in between, and we have then the via made of copper. And the problem is that we have with the solder joint that during current transfer we have a high expansion of materials, especially if we get a lot of heat into the solder joint. We have also really high expansion due to high cross sections of the materials. And as we can see here, the coefficient of thermal expansion for copper and for brass as a copper alloy is quite similar, but the coefficient of thermal expansion for solder tin is completely different. And when we get a lot of thermal cycles, we get the expansion here, and the expansion is different. And after these thermal cycles, we can get a cold solder joint, and this is the result of many expansions, and finally the solder joint breaks. And if we have connectors for signals, for example, it's not a big problem that we can't transfer signals. But if we have connectors for high currents, the result of such cracks is very high resistance, and with the high resistance there is a lot of heat, and the PCB can be damaged or can burn down. And this is the main problem of the cold solder joints. We don't have this cold solder joints with the press fit technology, and that's the point what is making the press fit technology that reliable. Another problem with the cold solder joints is also that if we solder, we can't really look inside the solder joint, and sometimes it can happen that the solder is not getting properly inside. Again, for signals it would work, but for currents, we want to transfer current into the layers. But for example, here the current is coming here. It wants to go into the layers, but it's not possible because here is no connection. So the current is flowing through this little solder area, and solder has also about 10 times higher resistance as copper, for example. And then it flows through this point into the layers, and of course we generate a lot of heat here. And then this can be a final result of such bad solder joint. Exactly. Are there any questions regarding reliability of press fit technology?
At the moment, everything seems to be clear, Vladimir.
All right. So another very common question is regarding requirements on the PCB side for the press fit technology. And yeah, we have special requirements. We have also specifications in our data sheets. And here I want to show you how a via is created. So first of all, we have to drill a drill hole into the via through all the layers. After that, we have to plate copper to connect the layers in between. And here we need a copper thickness of at least 25 microns of copper, because as we saw in the cross section before, in the cross section of the press fit area, that we are cutting with the pin into this copper. And as more copper we have here, as more comfortably we can press into the PCB. And 25 microns is the minimum, but some PCB manufacturers have only 17 or 18 microns in usual PCB manufacturing process. So if you order PCBs from your manufacturer for press fit technology, you have to tell them that these vias are for press fit technology and they should have at least 25 microns. Optimal value is 30 to 40 microns here. And after we got copper into the plated through hole, we need also plating for protection of copper. And there are different platings possible, like gold plating or tin plating. For the press fit technology, the best is chemical tin. And the more interesting is for us then the final size after the drilling, plating with copper, plating with tin, and then the final size is the most important, because to this final via we connect our pin finally. And here are different PCB plating processes for tin. So why we suggest chemical tin process, chemical tin plating, because in the via with the chemical process we have constant tin thickness to the copper, and this thickness is usually for chemical tin between 1.2 microns, 1.6 microns in general. But we also have hot air leveling, and this is a mechanical plating process. And we can see here that the tin thickness is not constant. And if we get too much tin in the via, we press our pin inside the via, and we need to deform this area, and we remove this additional tin, and we create some chips, some metal chips. And we don't really want these metal chips on the PCB or in production process. So we need after it additional process of cleaning or we need to close the chips with paint or something else. So, and here you can see the PCB specifications that you can also find in our data sheets. We have this specification for chemical surfaces like nickel gold, and for chemical tin. And here is the specification for hot air leveling. And you can see here the via is smaller because you automatically generate more tin while plating process. And you can also see here the drill hole size, and we suggest to use this drill hole size with 1.6, and we want to push the PCB manufacturer to get more copper here, because you can also get this final via with a smaller drill hole size, like 155, but then the PCB manufacturer can put less copper into the via, but we want to have for the press fit technology more copper in the via. So that's why we suggest to drill with 1.6, and then we hope that PCB manufacturer will plate 30 or 40 microns into the via to get the best results during press fit process. But the minimum value is 25 microns of copper. And here we can see, yes?
I have a question coming in here, fitting to the plating. So it is what is the main difference in the results if you use ENIC or if you use tin plating on the PCB due to the hardness of the nickel?
Yes, that's exactly the point why we suggest to use tin plating, because the nickel, the problem is not the gold, the problem is more the nickel, and nickel is very hard material. But for the cold welding, we need soft materials to get high frictions and to generate optimal cold welding. If we have nickel here in between on the ENIC plated PCB, so the friction is less, and the cold welding is not that good like we have with the tin plated PCB. And finally, the holding forces are also less when we compare ENIC to chemical tin, but the holding forces of ENIC are still enough to fulfill the requirements of the press fit standard. All right.
Thanks.
Okay. Here we can see again the cross section of one pin of the press fit area, and we can see here that the copper thickness here is 40 microns, and this is actually a perfect press fit connection. We can see here we have a huge connecting area on any corner. We have here some angles with 90 degrees. Here we have 18 degrees. We can see here the final via size. It's 1.44 millimeters. And we see also here that here is a lot of copper left, and we don't touch the FR4 material. So this is how a press fit zone should be like. And here you can also see why we suggest more copper in the via. So if you have more copper, you press more against the copper, and if you have less copper, then you would probably touch the FR4 material. It's also not that critical if you touch the FR4 material because you can see here we have less copper as here, for example. But even if you would touch FR4 material here, here on the sides, because you are cutting more deeper on the sides, you still have a lot of connection to the copper of the via. So it's not really critical. The only disadvantage is if you press too far into the FR4 material, you could generate cracks, and cracks are not allowed according to standard. But in case of functional question, it still would work without any limitations. You can see only the cracks mostly in the cross sections like here, but in the practical point, you will not see any issues. Another very common question is, what are the requirements for the layout? First of all, we have also other parts on the PCB, and we need to keep distance to other parts, and we need to keep at least from the edge of the via at least 3 millimeters to other parts, and then you can already place SMT components like you see here. The same is the distance to the edge of the PCB. If you would have an edge here, we need to keep 3 millimeter distance to the edge of the PCB. Then we need proper layers to transfer current on the PCB, and because of the high current flow, we need some copper around the part, and we suggest to have 3 times wider layers as the part itself. So this part is, for example, 10 millimeters wide. So layer width that we would suggest would be 30 millimeters, so 10 millimeters around this one, because the main limiting factor during current transfer on PCBs is the PCB itself and not the REDCUBE, because the layers are quite thin. So if you have 70 microns, for example, it's only the thickness of a hair. Yes, and that's it. Maybe for high voltage applications, you need to keep the creepage and clearance distance according to your voltage. If you have higher voltage, you need bigger distance. If you have lower voltage, you need less distance, because the parts are non-insulated. So you manage it only through the distance to other components, or if you have plus and minus here, then you just generate it by distance. All right, any questions at this step of presentation, Thomas?
Yes, so the question is, can I also press into massive material like copper bars, and what do I need to take into consideration?
Yes, of course. Maybe we go back to this one. Of course, you can press into copper bars, because the copper bar is nothing else as this one, but instead of FR4 material, you have just copper here. And it's even easier to press in the copper bars or in the brass bars. It's also possible to press in the brass bars. The only thing we suggest is to use also some plating on copper bars or on brass bars, but it also depends on the application itself, if you need the plating or not. But with the plating, you can be really sure that there is no corrosion during the period of life of the connection. What you need for the drill size for the copper bar is the same specification like we use here. It doesn't matter which one you choose. You can use this one or this one. It's not critical with copper because we can't damage any FR4 material. So even if you use a smaller size like this, you just have more deformation in the copper, and that's it. So it's not a problem to use it with copper bars or brass bars.
Thanks, Vladimir. I have another one coming in. Why using this material for insulation yet far many implications is the question. So for insulation, I think it's dedicated to the tin you talked about for the outside insulation.
I didn't really understand the question. What is the topic about? Why we don't have insulation on the REDCUBE, or?
So I'm not pretty sure. It's why using this material for insulation, yet far many implications. Maybe there could be some additional explanation to this question that would be very helpful. Meanwhile, I could switch to the second one, and maybe we get a little bit more information on the first one, if it's possible.
Yeah, maybe because I can't really understand what the person is asking for to explain it.
Yep, same for me. So I take the second one, and maybe we can get some additional information.
All right.
The second one is, we don't have a press fit process in the production. We would like to use SMD THR and wave soldering. How much current derating needs to be considered with different material expansion and solder height to have a proper system?
Yeah, that's actually a good question. Then we need to go back a little bit to the soldering again. So I would probably start with the SMT components. I don't have a picture for it at the moment, but maybe you can imagine it. So usually if you solder an SMT component, then you solder the SMT component on the top of the PCB. And so it means all your current is coming here to only first layer. Additionally, you have solder in between. Yeah, for the SMT component, you have solder here. So, and with the solder, as I told before, the solder has up to 10 times higher resistance as copper itself. So you have automatically higher resistance. And you also need to bring all the current down in the other layers. And it's not that easy because you are not really connecting directly into all layers. You need more small vias around the solder part. And then you, of course, have also the solder with higher resistance. So with the SMT components, you are quite limited. And especially for high currents, you need big cross sections because you have high currents, and with the cross sections, with bigger cross sections, you have much higher expansion. And especially if you have thermal cycles, and you mostly have thermal cycles when if you transfer currents, you have a lot of movement in the solder joint, and this makes this technology not perfectly reliable for, especially for applications with a lot of thermal cycles. So from my experience, we say that soldering technology is limited at about 100 amps, and everything above is quite dangerous to solder because of a lot of thermal expansion during the lifetime, and also it's difficult to control the solder joints, also in the SMT solder joint or in a THT or THR solder joint. You can have air bubbles in it. The solder joint can be not perfect, and then you increase your resistance again, and that makes it a little bit dangerous. And as mentioned before, if your solder joint is not perfect, resistance is increasing and the whole application can be damaged. So the number for current is about 100 amps for soldering technology. You can also see it for our product group because we are able to manufacture bigger parts for soldering. We also would like to sell them, but it doesn't make sense. Also for SMT components, they are too big then. You are not able to pick and place them from the reel because they're too heavy. You need more heat in the soldering profile. So there are many points that don't really make sense to use these bigger parts for high current in a soldering process. All right, I hope I could answer the question completely. It's quite huge area, and we could discuss longer about it, but probably we should go on with another questions.
Yeah, I have two more for you coming in.
Yes.
First one is, how could I calculate current capability of screw connections?
Yeah, it's difficult. First of all, you need to know the ambient temperature. You need to know all the cross sections of the components. Then you need to know the delta T, so the allowed increase of temperature that you allow in your application. And it's not that easy to calculate it because there are many parameters. You have also different parts on the PCB close to your other components. And the easiest way to do it is starting with the cross section of the cable. And for example, if you have 100 amps, you need a cross section of the cable of 16 millimeter per square, for example. And then out of this cross section, you can also take a look on the cable lugs, and then for 16 millimeters per square, usual cable lugs are like M5 or M6, and out of this thread size, you can take a look on the components itself and check the specifications, check the current specifications, and then choose the right part. That would be my suggestion.
Thank you. And the second one coming in was, what are the tools recommended for pressing the parts in?
All right, that's a good point, because it should be the next topic in the presentation. Yes, what tools do we need? First of all, we need a press. It can be a manual toggle press, or it can be a automatic pneumatic press like we see here in the video. Then we need a support matrix. It's really important to use a support matrix to support the PCB against bending. And here we also can see this guy is pressing a REDCUBE component through the PCB into a copper bar. And I will just show you the video and just take a look. Yeah, here is the copper bar. Here the PCB is coming on the support matrix, then the components, the stempel, and then yes, that's it. That was a press it process. We can also here on another slide, this is a manual press. We can see here a sensor that we use for the monitoring of press fit forces. This is really important to do it, because then we have 100% control, quality control, and this is the best way to control your process. And here on the matrix, you can see that we need for every pin a single hole just to support the PCB against bending and breaking. Here are the technical process parameters. As we saw in the first, on the second slide, we saw the press fit curve, and here you can also see the maximum press fit forces that are depending on PCB thickness, and also depending on the lower limit of specification, upper limit of specification, and the nominal value. And here you can see the range of the forces where they should be for the particular PCB. And it's different for ANIC, for nickel gold, for HAL, and for chemical tin. The press fit standard is also specifying these values, that the minimum press in force should be at least 14 Newton. We usually have much more, it's about 100 Newton. And the extraction force is at least 30 Newton, but usually for our components, the extraction force is the same like the press fit force. Yes, that's it about the common questions we get from the customers regarding press fit technology.
Nearly.
Any other questions so far?
Yes, I still got one. I just didn't want to disturb you. The question is, do I always need a stamp to press in the components, and where do I get it?
A stamp is not always needed. It depends on the part itself. If you have a part with internal thread, you don't need a stamp. But if you have a part with outer thread, you shouldn't press on the thread itself, on the thread shank itself. So you need a stamp. and the stamp you need to organize yourself from your EMS or from a metal company that can manufacture it for you. So it's depending on the press itself, and it's also depending on the process. It's also sometimes depending on the parts close by. If you have bigger or smaller parts, do you need a tiny stamp or a bigger stamp? So that's why we don't offer this type of tools, because it's individually in many types of applications.
Thank you very much. And I have a last one that came in for the moment.
Yes.
This is going back a little bit to what we had before. Is there any specification on the FR4 materials for the PCB regarding the press fit?
No, there are no special requirements on the FR4 materials. So usually all standard FR4 materials are okay. The only one is if you use the PCB with high T key. I don't know exactly the English word for it, for high temperatures. So there is some ceramic into this FR4 material. So it's better to have more copper in applications like this. To go with 40 microns, for example, would be suggested for a PCB like this. But in general, in the most applications, you just use a normal FR4 material like for all other components.
Thank you, Wladimir. Yeah, that's all questions I have at the moment. And I would say we are just in time. So do you still want to add something?
Yes, maybe one thing I would like to add is regarding toolings, and especially for the matrix. You can use also for prototyping, for example, because usually you need some tooling for prototyping, and for the stamp you can use also 3D printing if you have hard plastic. So you can do this matrix out of 3D printer, and also the stamp just for prototyping. It should be enough. But for series you need a very hard material. Even aluminium is too soft. So you should use something like steel that is not deforming over the period of many press fit processes. Like if you have few thousand press fit processes, it can deform because you generate some force through the PCB over thousands of cycles. I guess that's it.
Okay, so thank you, Wladimir, for doing the presentation, especially for answering all the questions in detail. And so now I think we are finished with our webinar. And if you have any questions left, we will answer them via email afterwards, of course. Thank you very much for your attention, and I hope you enjoyed the webinar. So
thank you
please
from my
let
side
us know even afterwards if you have questions.